Good day all, and welcome to round 2 of the compressed air purification webinar. Since we have a filled webinar today, I'm gonna commence instantaneously. And initially, I'd like to introduce some of our panelists. We have Russ, which is going to be assisting in this webinar presentation. And we have Nico Floresco. You may have had the pleasure of attending his previous webinar, which was on pressure vessels, and Anita Gupta. She's the filtration sales manager and also the person that gave a pleasant webinar on liquid filtration. So today's topic, again, it's going to be consisting of compressed air and moisture, contaminants, and compressed air. And this illustration is just to show that, you know, even though air may appear to be nice and clean, sometimes there's moisture in it. Other could be chemical contaminants, particles, shad flies. It could be consisting of anything. And as a brief recap, on our previous presentation, we discussed compressed air theory, the effects of compression, temperature, dew point, relative humidity, and relative humidity is relative to a certain temperature. It's expressed as a percentage. And today we're going to be more elaborating on the effects of how to filter all these contaminants that are in the air. If you'd like to have access to previous webinars, you can go to the site illustrated on the screen, and you can access upcoming webinars and also see some of the previous ones that were already given. Basically, today's outline consists of ambient air filtration, compressed air separation filtration, and then compressed air dehydration. Ambient air filtration is at 0 psi. Compressed air filtration and separation would be more removing liquids and particles out of the air using filtration, separation. And then there's compressed air dehydration, which would typically be something like a refrigerant dryer or DESICCANT dryers, something that removes the vapors out of the compressed air. And at the end, we'll have a few moments for some question and answers. Basically, there's a chain of events that takes place when we want to purify air. We have air coming in from the compressor intake. So theoretically, the air should be relatively clean. It's coming from outside, but in reality, there is certain dirt, water, vapors, hydrocarbons, and they're at 0 psi because they're at the compressor intake. Then it gets compressed to 100 psi or higher. The consequences of that is the temperature increases when you compress air, and then the air is used for point of use. If we don't remove the contaminants out of the compressed air, you can have product spoilage, you can have line freeze-ups, liquids in your airlines, bacterial growth, erosion, corrosion. So the goal of today's presentation is to assure that the air quality is adequate for the use that you're going to be using the air for. In the compressed air system, there's basically, we're going to split it up into 2 zones. And the first zone is the ambient air filtration and compressed bulk water removal zone, consisting of these 4 components. So you have your air intake, the compressor, the compressor, the water-cooled aftercooler, it could be an air-cooled aftercooler, the separator, and a pressure vessel or receiver.
Zenon, if I might add, the arrows, and this is my fault, the arrows should be reversed on that water-cooled aftercooler.
Correct.
The water should be coming in upstream and leaving downstream.
Yeah, exactly.
Just
it should be countercurrent to the direction of the flow air. Good point, Russ. Well, I'll have to modify that for the next presentation. So as illustrated here, the first stage is the ambient air intake particulate filter. And it could consist of something as a, pleated media filter that removes particles down to anywhere between 2 and 10 micron. And it could be something as simple as a cartridge type filter, and as complex or as elaborate, for a filter used for gas separation plants. And as illustrated here, you notice that typically these units are at an elevated position. We try to keep them at least 10 feet or higher above ground level to minimize the potential of particulates being drawn in. And also you notice that there's some baffles to prevent rain or snow or other particulates or contaminants from entering the air inlet filters. So that's the standard basic, air inlet filter concept. But then we're not always lucky to have nice clean air. So, I titled this one, Air Intake with Issues. And some of the issues that we are faced with, specifically here in Canada, is that during the winter time or just prior to winter, when the temperatures get cold, there's the potential of frost buildup on the air intake. And if you have a certain velocity and a certain temperature moisture content, frost would build up at the air intake. To prevent that, John Brooks designs with SPX, or in this case Dollinger, heater elements that prevent frost buildup, or they even use the hot oil or the hot gas from the compressor to prevent freeze up at the air inlet. The other part is that there could be chemical contaminants or acid contaminants that are present in in the ambient air. And to prevent that, we use a scrubber to prevent chemical going downstream. The benefit of that is these acidic chemicals would corrode the metal, the compressors. And Russ, what is that material they use there? That beautiful pink colored stuff?
Let's see if I can pronounce it properly. Potassium permanganate.
Okay.
It's close enough.
It's good you can pronounce it, because I'm sure I'd get it wrong. Yeah. So it's basically, and in other circumstances, we may use carbon or potassium, I won't use the second word, to prevent acid buildup from the air intake to the compressors. Other issues that arise is if you have high dirt levels at your air intake location. There's multiple methods to minimize the high dirt levels. So typically air intakes consist of panel filters, and these panels could prematurely block if you're in a sandy area, high dirt level area, certain mining areas. So as a pre-filtration, we would install a spin filter that knocks out particles in approximately, if I'm mistaken, 10 micron and larger. And that's like a first stage filtration prior to the panel filters. Another method for high dirt level locations is pulse jet filters. So they're self-cleaning. We've installed some of these in basically Saudi Arabia was one of the locations for dust storms. And they're self-monitoring. They clean themselves. So sometimes they don't have to work at all because the conditions are clean, but if dirty conditions arise, then they would clean themselves. And if I get this right, we can show a little animation. And if you have headsets on, I'd recommend you potentially take them off. I'll just stop that. Oops. Just go back for a moment. And Russ, you were mentioning one time those pulse jet filters, they work in sequence, so they're not all pulsing at the same time.
That's correct. So what happens is what you were seeing there is a reverse flow pulse of compressed air. and the shock it creates as it goes through the media actually loosens and causes the debris to fall to below the filter. So sometimes customers have a container there where they can catch the dust or whatever. But when you see the rows of filters hanging down from the housing, what happens is these are there's a controller on the unit, and these are cleaned in sequence. So you might have a row of 6 or 7 of these, do that reverse pulse, and then 5 minutes later you might have another row and another row, depending on the dirt load and how it's set up. So it's a continuous operation whereby the customer, in a case of a high contaminant or high dirt area, can continue to operate for long periods of time without having to do the maintenance on filters.
And these would typically be installed in locations where they want to minimize human intervention, so they're self-monitoring, self-cleaning, and typically the duration of these elements easily exceed a year. Sometimes I've been told that they exceed, 3 to 5 years, but it's always dependent on the dirt levels. And since they're self-cleaning,
it also depends on how the cake builds on the media and what type of dirt it is. Because if the cake builds a nice layer on the surface of the media and doesn't actually penetrate the media, then it's easier to remove it, and the media will have a longer on-stream life before you hit a terminal pressure drop.
Yeah.
So when they size it, what they want to do is take a look at the dust and size the filter so that the dust or dirt or contaminant actually cakes on the surface of the media and doesn't penetrate the media and start to block up the pores.
I'll go to the next slide. So the goal of, cleaning the air is to, one, protect the compressor, minimize the dirt load. And here we see a animation or visualization of a compressor, and the blue quadrant is, nice cool air coming in, and coming out, we got hot air. Basically what occurs is that you're concentrating the contaminants, the water load, the chemicals, the hydrocarbons sevenfold, because you're taking air from an atmospheric pressure of 14.7 psi, compressing it to 100 psi. So that's approximately a factor of sevenfold. So the concentration increases of your dirt, your acids, hydrocarbons. But since the air is warm, it can hold more moisture in it. But our goal is always to try to get the air as clean in stages as much as possible prior to the compressor, just to minimize the dirt load. Just get this here. This illustration basically shows us that, the compressor, after compression, can get the air temperature up to 250 degrees Fahrenheit. It can even get hotter depending if it's a single stage compressor or multiple stage compressor that have intercoolers. And you would have like a cooling liquid, either it could be an air-cooled system or a water-cooled system, and we would try to get the air temperature down as low as possible. Typically compressed air systems are designed to accept the maximum inlet temperature of 100 degrees Fahrenheit. And the logic behind that is, as illustrated here, at 100 degrees Fahrenheit, we have approximately 21 grains of moisture per cubic foot. If you can get the temperature down to 80 degrees Fahrenheit, you only have approximately 11 grains of moisture per cubic foot. So you've lowered the moisture level down by 50%. Benefits of that is then the filtration can take place in a separation manner, in a filtration manner. You don't have to use a dehydration system because you're converting those vapors from you're converting the water from a vapor into a liquid form, and it's a lot easier to remove liquids than it is to remove vapors, and it's more cost effective to remove them in a liquid form. Russ, you were indicating one time that there's water cooled after coolers and air cooled after coolers, and I guess the benefits of air cooled is that the air is sort of free for cooling it, except for the motor.
Yes,
But
and the main difference that I see is, you know, if you have the water available, it's always better to use a water cooled, because the approach temperature, or the temperature at which your 250 degree F inlet air, if you look at the approach temperature that a water cooled aftercooler provides, is around 10 to 15 degrees F. So if you had 60 degree water in this case, and 250 degree F coming in, you would end up with an air temperature of 75 degrees F, right? On the other hand, if you had an air-cooled aftercooler, it probably has a 25 degree temperature approach. So if you came in at 250 degrees F with a 25 degree approach on an 80 degree day, your outlet air would be 105 degrees F. So, you know, as Zenon mentioned before, we want to get this air temperature down, not only for safety reasons, but also to condense as much of the vapor as we possibly can, because it's easier to take out liquid.
yeah, good point. So then the consequence is, now that we've taken that hot compressed air and cooled it down to, let's say, 100 degrees Fahrenheit, you know, we have to knock out that moisture somehow. And typically the first stage of moisture removal after an air-cooled aftercooler or water-cooled aftercooler would be something like a cyclonic separator, as we see illustrated here. The benefits of cyclonic separators are that they remove 99% of your liquids, 10 micron and larger. They basically have minimal pressure drop. They have no elements to replace. So it's using a mechanical or centrifugal force to knock out the liquids and knocks out some of the particles. So this way, equipment downstream of this component doesn't block as quickly, has a lower pressure drop, and it's just, I'd say, a very energy efficient manner to do this. And so one of the brands that we distribute is the Eaton brand, which is highly recognized in the industry for this design of separation. And yeah, as stated here, then it can also have a integrated sump just to accumulate the liquids, and then it's drained on a regular basis to eliminate the liquids from the separator. And typically the following stage downstream of a separator is we would install a receiver. Again, the benefits of a receiver, it could be considered a bit of a knockout drum, or it's also used to assure that the compressor isn't loading and unloading too much. And in the past, this was a mandatory component prior to a DESICCANT dryer to minimize the pulsations from piston type compressors. With the new technology or newer technology of screw type compressors, the flow is a bit more smooth and doesn't have much of a negative impact on the air dryer, DESICCANT air dryers, but still highly recommended to, one, cool the temperature down a little bit more, makes the compressor load and unload less often, so less issues with the starters. Just doesn't have to be too big, but they're typically sized for the capacity or design based on the requirements of the compressor.
Hey, Zenon, these ones shown on the truck here, are they made at the John Brooks facility?
Yeah, that's correct, Russ. That's made by our ASME fabrication shop, MDA. So yeah, these are some of the receivers, and yeah, these are of some substantial size. Then now we're going to get into the second zone of air purification. So the first zone was removing, you know, ambient air particles, bulk liquids, and now we're getting more into the polishing almost stage of the compressed air purification zone. And typically that consists of a coalescing filter, some sort of dehydration system. So it could be a refrigerant dryer or DESICCANT dryer. In certain circumstances, we would put a carbon absorber if you don't want to have any hydrocarbons, and an after filter. And we'll go through each one of these gradually. Here we see our coalescing filter, and basically, the goal of the coalescing filter is to remove any residual liquid or any residual aerosols that the separator and the receiver have not removed. And as Russ was one time explaining to me that, even downstream of the receiver, the air can cool a little bit, so some aerosols can still occur. And Russ has a very
so what
proper manner of explaining this concept.
Yeah, the aerosols can still be there, but there can also be droplets there depending on the size of the receiver and the velocity of the air going through it. The residence time doesn't necessarily mean that you're going to take the liquids out if the receiver's undersized, but the coalescing filter is when you're talking about air purification or desiccant dryers. This is the most important component of the system that we're going to look at. What's happening, or what the artist is depicting on the left. The yellow lines are supposed to represent filter media. The green dots are supposed to represent droplets and aerosols. And all a coalescer does is process or sort or take small aerosols and droplets and turn them into large droplets, so that by the time as the air passes through the media and pushes the liquids through, the droplets are large enough and they have great enough mass to fall to the bottom of the housing, which is depicted in the drawing on the right, which shows the droplets on the outside of the filter cartridge. So the drawing on the right shows a cutaway of a filter housing with the flow coming in at the bottom and leaving the housing at the top after it's passed through the core of the filter, through the layers of media to the outside. And there is a metal support core on the inside of the filter element and a outer metal cage on the outside of the element to support the media so it doesn't move. The only other sort of makeup of the filter element is the final classifying layer where you see the droplets. And that layer allows the droplets to run down the outside of the cartridge and form in the lower third of the cartridge. The reason we do that is we want those droplets to fall to the bowl of the housing, but we don't want them to be re-entrained where the air velocity at the top of the cartridge or leaving the housing is a lot higher than it is at the bottom. So we want to form those droplets on the outside of the coalescer at the bottom. The only other point to look at with a coalescing filter is coalescing filter ratings. And I like to see a coalescing filter that's rated based on its ability to remove liquids. So if you come in with 20 parts per million, the ones that SPX makes will deliver 0.001 parts per million. So that's quite a significant drop. Some people, when you look at coalescing filter cartridges, they're rated by micron size. And in fact, it will stop particulate, but a micron rating is a particulate rating. This filter, if you don't have any particulate, will basically process this liquid forever. It's not stopping anything. The only thing that causes you to have to take out or remove a coalescing filter is if there's particulate, rust, pipe scale, something in the line where it captures it in the filter and causes the pressure drop to rise. So the other thing you want to look at when you're evaluating a coalescing filter is how much surface area does it have, because that's going to dictate the initial pressure drop and how long it can stay online and its dirt holding capacity before you hit a terminal pressure drop.
Hey Russ, that's a good point, because it just makes me think the better we can filter the air, prior to the compressor, if you have the proper metallurgical, if you don't have the acid coming in that's corroding your vessels or causing damage to the compressor, then in theory, these filters should have an infinite life because, like you stated, their goal is to remove liquids. And in theory, there should be a minimal amount of particulate, but in reality, we always get something in there. And
yes. Yes.
They typically last, minimum a year, if not longer. If they're lasting less than that, then there's some other issues prior to the compression stage or during the compression stage. The customer should be looking at, what's going on with this compressor.
Yeah, we've had a few cases in the field where customers having short life on a coalescing filter, and what they'll do is simply place one of those Eaton separators, upstream in front of the coalescer to knock down rust, pipe scale, whatever kind of contaminants causing the coalescer to build pressure drop. And usually the cost of putting in the Eaton system actually is paid back in a short period of time because the coalescing filter doesn't have to be changed out as often.
Yeah, good point. Yeah. Then we get, downstream of the coalescing filter, then we get into the purification zone. And the most common type of purification systems that actually lower the dew point would be either a refrigerant dryer or a desiccant dryer. Each one has their pros and cons. I'm not going to get into the financial aspects of one or the other today. I'm going to save that for round 3. But basically, a refrigerant dryer has its limitations, and the limitation is it can't get the temperature down below 35 degrees Fahrenheit or approximately 2 degrees Celsius. If it would get the temperature down below that zone, then you would have freeze up of your heat exchanger. The benefits of a desiccant dryer is that it doesn't use condensation or cooling thermal energy to remove the moisture out of the compressed air lines. It actually uses absorption. And I'll get more into that on the following slides, but it's just to show that most 2 common systems available on the market are either refrigerant dryers or desiccant dryers, and they're honestly dependent on the outlet dew point you require. So refrigerant dryer, plus 35 to 40 degrees Fahrenheit. Desiccant dryers, you can go, most standard is minus 40 dew points. In certain circumstances, we go down to minus 100, in the northern conditions of Alberta. That seems more of a standard that they want it cooler than the minus 40. But we can get it as dry here from a moisture content as nitrogen, which is typically at a minus 100 dew point.
Zenon, for those that weren't on the last seminar, where we covered some of the details on dew point and everything. Dew point is the point at which water will condense at a given temperature. So that's not the actual temperature of the air downstream of the dryer. It's the point at which any remaining vapors would condense.
And here I'm just showing again the various zones. So we're going to be just elaborating a bit more on the purification zone. What we always like to do is, assure that that coalescing filter is there. As Russ mentioned earlier, it's the last line of defense to remove liquids, aerosols, and the better we can filter those aerosols out, specifically if they're oil, the longer life you have on the desiccant life, the better that we can remove, aerosols out of the system prior to refrigerant dryer, then there's less fouling on the heat exchangers. So it's always sort of critical to have a good coalescing filter, just to minimize or improve the efficiency of the purification system.
Zenon, just as another point, when the purpose of the coalescing filter, as we've mentioned, it's important, it's to take out liquids and aerosols. But ultimately, once we leave the coalescing filter, the air still contains vapor. And that's what the twin tower dryer will remove, is vapor. It will not remove liquids, as we know. But I just want to make that point, is once you get to the twin tower dryer, if you've got liquids in the line, they'll go right through that dryer.
I agree. And apart from just going right through the dryer, then if it's a desiccant dryer, it can also destroy to a certain extent. If you have oils in your liquids, then that can destroy the desiccant. And I always like to bring up, one of the most important components I find on the compressed air purification system is this very economical drain valve. If this fails, then you can have liquid oils, and as you previously stated, the desiccant dryer is not made to remove liquids. So this would overload the dryer from a liquid standpoint. Also, with new technology today, and we'll elaborate a bit more on that on the next seminar, is that in the past, they were always timer-based drains. So, with seasonal changes, the amount of liquid coming out of the drain valve varies between summer and winter time. In the winter time, the air at the inlet to the compressor is relatively dry. In the summertime, it's very hot and humid. So the amount of liquid coming out of that drain valve changes quite drastically between seasons. And with new technology, it's almost a cost-effective upgrade to put no-loss drain valves that actually detect the amount of liquid in the sump or in the exhaust of where we have to drain that liquid. I'm just going to elaborate a bit on the function of a refrigerant dryer. And basically, as previously stated, we downstream of the compressor, the temperature could be 250 degrees Fahrenheit. Goes through the water-cooled aftercooler or air-cooled aftercooler, gets it down to approximately 100 degrees Fahrenheit, and then the function of the refrigerant dryer is to further cool it. So we use an air-to-air heat exchanger, basically gets the temperature down from 100 degrees Fahrenheit down to 60, 70 degrees Fahrenheit. Yeah, and then it goes through the air-to-freon heat exchanger, and this one will get the temperature down to approximately 35 degrees Fahrenheit. Can't go much lower than 35 degrees Fahrenheit because then the liquid or the water will start freezing up. So the limitation is about 2 to 3 degrees Celsius. Downstream, now we've condensed all that vapor into a liquid form, goes through a mechanical separator, knocks out the liquids. So it's saturated here, liquids coming out. Downstream of the mechanical separator, basically we only have vapors at that stage because all the liquids got knocked out. And then we're using that cool 35 degree Fahrenheit air to pre-cool the hot air coming in. So it just makes it more energy efficient. And we want the air coming out or the line coming out not to be at 35 degrees Fahrenheit or 3 degrees Celsius, or then your pipes would start sweating because you would get condensation on the exterior of your pipes from the cool air coming out of the refrigerant unit. Anything to add on that one, Russ? Or you think I covered
it? I think that sounds pretty good. I mean, the point here is you would select this dryer based on an application where it wasn't critical downstream. Because if your application is far away from the dryer, you may get some moisture at the point of use. So this is highly dependent on the nature of the application. Or again, if the air is coming in contact with the product, or if there's some kind of critical application that would negate the use of this dryer. But our company makes about 30,000 of these refrigerant type dryers worldwide every year. So there's all kinds of applications for them. It's just when you get to a certain type of application, you have to go to a desiccant type dryer in order to drive the dew point down further.
Good point, Russ. Like, for Canadian climate, we would never want to use these if your airlines are going outdoors. Because I don't think there's anywhere in Canada that the temperature doesn't go below freezing point. So this would be a definitely negative design for outdoor line applications. Then the next design that is very popular is the heatless dryer design. And typically desiccant dryers, their design concept is relatively all the same. You have prior to the inlet, you would have your coalescing filter, have saturated air coming in just in the vapor form, goes through one chamber, lowers the dew point from saturation or 100 degree Fahrenheit dew point. Once it gets absorbed by the desiccant tower, the dew point coming out would be at -40 degrees Fahrenheit, and air would go to the point of use after passing through an after filter. And we'll elaborate on the after filter a bit later. But the design concept for these units is that we take 15% approximately of the compressed -40 dew point air and expand it to an atmospheric pressure. So you're taking one volume of air, expanding it to 0 psi, so you get 7 volumes of air, and that's why you only need approximately 15% of that compressed air for regeneration purposes. And by expanding it to an atmospheric pressure, you get a -70 dew point, -70 degree Fahrenheit dew point. So it's substantially drier than the moisture content on the desiccant. And it does basically like a backwash, and it purges out. At this location, there would be a muffler removing the moisture off the desiccant bed. And as stated here, atmospheric volume is 7 times larger. So the dew point goes from a -40 to a -70, and that just does a very efficient backwash. And on heatless dryers, they change chambers from one chamber to the other approximately every 3 minutes. If you want a -100 dew point, then it would be changing chambers every 2 minutes. And very good concept, very reliable equipment, except the negative aspect of it is you're losing 15% of your compressed air at 100 psi. But it's still one of the most reliable designs, and depending on the flow rates, I'd say below 1,000 SCFM, this is typically the design standard that customers use. Then once we start getting into bigger designs, this unit starts at 500 SCFM. A heatless dryer, you can get it from 2 SCFM up to most likely 15,000. But at the higher velocities, it doesn't become very cost effective. The capital cost may be less, but the operating cost would be substantially more. Once you start getting into higher velocities or flow rates, then heat reactivator, blower design dryer is more of interest because the energy cost payback. And Russ, I know we had the pleasure of working on a certain project not too long ago where we're in the process of fabricating, or SPX will be fabricating a very large unit. Maybe you can elaborate on the design of these units. And
yeah, no problem. So yeah, as Zenon mentioned before, now when we're looking at twin tower dryers or desiccant dryers, you have to start looking at the flow rate and the energy cost. And I guess we're going to talk about energy cost in more detail on the next webinar. But here in particular, when you're looking at a heatless dryer versus a heat reactivated or externally heated blower purge dryer, the difference is when we get into higher flow rates over, let's say, 1,000 SCFM, I like to evaluate both systems before we quote. The heatless dryer is less expensive. However, its energy consumption can be a lot higher. The 15% purge is a stumbling block for some customers, especially when they get into flow rates of 10,000 SCFM, things like that. So the fact that this type of design, the biggest difference is you'll note there is no purge loss, or there is no 15% used up for regeneration. So how it works is the same way as the heatless. You have your air coming in at the inlet after it's passed through the coalescent pre-filter. Vapor-laden air enters the inlet switching valve. It's directed to the left chamber. When it's in the left chamber, as long as the amount of vapor in the air is greater than the amount of vapor on the surface of the desiccant will remove that vapor by adsorption. And the air will come out at -40, pass through the outlet switching valve, and downstream through the after filter into the point of application. So what you've done here is you've dried the air exactly the same way as a heatless dryer, but instead of using 15% of the compressed air to regenerate, here through the intake filter, the blower, and the heater, we take ambient air, we heat it up, and we move it through the chamber to basically liberate the moisture in the chamber. So So what we have to do in that chamber, and if you look at the diagram just above the schematic where it shows temperature rising from 0 to 150 degree F, what we're doing there is we're heating up the steel of the vessel, takes so many BTUs, we heat up the desiccant, takes so many BTUs, and then we need so many BTUs to drive off the moisture, and that's what's happening as we pass down that green line. You know, depending on how much moisture or vapor is contained in the chamber, that time can be variable. And at the outlet of the chamber, there is a heater termination temperature. So there's a method by which we read the temperature at the outlet of the chamber and we cut off the heating. So what happens with these dryers, as Zenon mentioned before, the heatless dryers run on a 3-minute or 6-minute NEMA cycle. These can typically, on fixed cycle, run on 4 hours of drying, 3 hours of regeneration, and an hour of cooling. And that drying time is totally variable depending on how much moisture is there and how much capacity the dryer has based on pressure, temperature, and flow. So when you get into larger flow rates, this is a very, very good way to dry the air because you don't lose any of the compressed air. The reason why we can have varying flow rates is we have a demand cycle control system called AMLOC, which monitors the amount of moisture in the desiccant bed and decides when it needs to be regenerated. So again, going back to what we talked about lowering the temperature at the inlet of the dryer, for every 20 degrees that you lower the inlet temperature into this dryer, you cut the moisture load in half. So that's why Zenon and I are always banging the drum about lowering the inlet temperature, because it just saves the end user a lot of money in regeneration costs. So what that probe that's depicted in the chamber does is measures the moisture front as it moves down the chamber, which may move all the way down the chamber in 4 hours, or it may move all the way down the chamber depending on flows, pressures, and temperatures. It may take it a few days before it needs to regenerate. So what we're doing is ultimately saving the customer energy. And we'll talk about that a little bit more in the next webinar. But in comparison, the heatless dryer is less expensive. And generally speaking, the heat reactivated or internally heated blower purge dryer is less expensive to run just because of the energy savings.
Yeah, I agree with that, Russ, you know, and sometimes customers don't take into consideration that, yes, the heat reactivated dryer is more expensive as initial capital cost, but then they can get a compressor that's, you know, 10 to 15% smaller in size. So if you do the cost difference, because now you're getting a compressor that's smaller in size, then the cost difference isn't as radical. And as we've seen over the past few years, you know, I guess in the 70s and 80s or 90s, you know, air energy cost wasn't as substantial as it is nowadays. So SPX and John Brooks, with our technicians that we have at John Brooks, we upgrade heatless dryers to more energy efficient units by adding these blower packages and like basically redesigning the regeneration concept to eliminate that 15% purge. So certain customers, instead of buying a new compressor, if they need more air, they can just add this blower package to their heatless dryer and reduce the purge consumption. So one, it makes it more energy efficient, and two, you're saving yourself 10%. So you're not buying yourself a very expensive compressor, you're just buying yourself a lower cost blower to increase the efficiency of your purification system. Excuse me. The next design concept that we have here is, I sort of call this one almost like a hybrid system. And you're using, you know, 6% of your compressed dry air to do the regeneration. So that would be similar to, you know, a heatless dryer where you're using 15%, but in this circumstance, you're only using 6%. And then in addition to that, we're using the waste energy of, and I call it waste energy because you're taking 100 psi air. So air is somewhat of a utility. It has a certain energy associated to it, and it's going through a venturi. So by decompressing the 100 psi to 0 psi creates a suction and increases the flow rate. And then that 15% basically goes across a heater and regenerates the desiccant bed. So yeah, I would call this sort of like a hybrid. It's taken a bit of the design aspect of a heatless dryer, a bit of the design of a heat reactivated dryer to do the regeneration of the desiccant bed. But as always, the design concept is relatively the same. You have your pre-filter prior to the inlet, you have saturated air going in, and then dry air and -40 dew point going out. Yeah, and then a certain percentage, or the 6%, is used for regeneration purposes and goes across the heater, creates a venturi, a vacuum. Basically, you're going from 100 psi across the venturi to 0 psi, and then it heats the desiccant bed and goes out the exhaust.
Then, and I guess the bottom line is here is every time that a customer comes to us with an application that's, let's say, over 1,000 SCFM, we start evaluating all these different dryers based on what the customer has as a resource. Can they afford the 15% purge, and or what size is the system? But it's all about, in the bottom line, it's all about what the energy savings could be. How much does the electricity cost to operate this heater during a year? And being as these systems often last in plants 20 or more years, this becomes very important if you're saving significant amounts of energy every year.
Yeah, that is true. And we'll see that on the following slide, but I just wanted to touch base on, you know, SPX and John Brooks, we distribute some specialty dryers. So if you have an expensive gas, CO2, nitrogen, natural gas, hydrogen, you don't want to be wasting any of that gas. So this is just another design where you'd still have your pre-filter, and this unit would have internal heaters. So it benefits of radiant and convection heat to do the regeneration on the regeneration cycle here. But basically it's similar to a heatless dryer, but instead of using 15% gas, you're only using 2% gas. So in the brewery market, this is very popular for carbon dioxide. And, you know, this way they're only consuming 2% of their carbon dioxide for generation. For nitrogen, natural gas applications. Natural gas, I guess it would be vented in a special manner similar to hydrogen, but this is one of the most energy efficient units, but at the same time, it is a unit that uses the minimal amount of loss of gas for regeneration purposes. As Russ was explaining earlier, you know, when a customer comes to John Brooks, then we elaborate or we evaluate on certain criteria. What's the design conditions? What's the application for? Is reliability the most important factor? Is it, you know, certain industries, even though the energy cost may be more elevated, they just have to have uninterrupted operating conditions, you know, annually. They can't have times for shutdown. So a heatless dryer would be more the design that a customer may be interested in, but then they have to take into consideration that the operating costs would be higher. So we evaluate all the factors, and so we can give the best recommendations for the criteria, for the conditions, for the industry that the customer is subject to or subjects us to. Hey, Russ, we're going to have to accelerate here a little bit. We're almost running out of time. But
yeah, I won't take too long here. I won't take too long here. We have a depiction of a housing. This would be the after filter. You'll notice the flow goes in the opposite direction from the coalescing pre-filter. The flow goes from the outside to the inside of, or the core of the cartridge. And the purpose of this element is just to remove any desiccant dust that may form over a couple of years in the twin tower dryer. So this is basically a particulate filter.
and these are often rated by a micron size. Typical is 1 or 2 micron. Most desiccant dust is 3 to 5 micron in size. So when you think of the human hair being 70 microns in diameter, and 40 microns being the smallest speck you can see with the unaided eye, we're looking at rating these filters, at least ours, at 0.9 micron absolute, meaning it'll stop everything 100, 0.9 microns and larger, 100%. So you want to look for something. The reason why we can give it an absolute rating is because it has fixed fiber, fixed pore size that won't change as pressure increases. Zenon?
Yeah. And the following slide is a depiction of, some of the units that we fabricate or SPX has fabricated in the past. And this will be similar to a unit that's going to be shipping to Canada in the next, I'd say, 6 months or so. Basically, this one's a blower regenerated dryer. So you see the blowers on the blue items there for regeneration purposes. And Russ, you're more knowledgeable about the design of this one.
Yeah, this is the factory has standard products, but we also build dryers to specifications that are provided for us or to us from customers. And in this case, they wanted a catwalk to be able to change the filters, to access the top of the filter housings. They wanted manways in the sides of the chambers, and a litany of other items that they wanted. And we have a whole engineering department that's very good and very experienced at providing this kind of setup. These I think these ones were built at our plant in Ocala and went to, I believe, Malaysia.
And on the right-hand side, we see a hydrogen dryer. So this would be somewhat of a specialty gas dryer. And this would be just to minimize the purge consumption. And this one has even like a little vacuum pump on it, just to assure that if there's any hydrogen, it's exhausted outside and definitely not kept in the facility. That pretty much completes our seminar for this round 2. The next seminar, the upcoming one, is going to be more relevant to energy costs, like basically equipment capital costs, utility costs, the costs of pressure drop, air leaks. As I initially stated, air is free, but once you compress it and purify it, it does have an operating cost. You need the electrical heaters to regenerate the desiccant, or you need the motor for the refrigerant dryers. So there's always costs associated amongst each design of dryer. And we're going to elaborate a bit more on that aspect, the operating costs of purifying air. So the most cost effective, I'm getting ahead of myself, so I'll save that for next time. And that's pretty much it. If there's any questions, and I'd just like to also state that some of these seminars that we provide, if they're relevant to your engineering profession, you can obtain from John Brooks a certificate of participation, and they can be used for your credits for hourly attendance, but they have to be relevant to your engineering domain, that it has something relevance to our presentation. So you can contact John Brooks, myself, some of my colleagues that are in your territory. And if you registered and supplied your email address, then we'll be reaching out to you to give you additional contact information. So basically, thank you for your time and using up your lunch hour, but this concludes our phase 2 on compressed air purification system.
If there are any questions, we have a few minutes.
Yep, we do.
Yeah. So,
and one of the questions is what is the expected pressure drop throughout a cyclonic separator? And I can answer this if that's okay. Now, the principle of determining pressure drop across the cyclonic separator, it is similar with respect to solid liquid separators or filters, in that the variables that you have to consider you know, their flow rate, line size, amount of moisture and contaminants. And to kind of give you an answer to your actual question, the typical pressure drop you can expect across a gas liquid cyclonic separator is less than 1 psi. We'd consider pressure as a particularly precious resource, and that's why we do have a means to oversize as necessary. And another question that we have is desiccant's life shorter with heated desiccant dryers compared to heatless type?
You want me to get that one, Zenon, or do you want to take it?
Sure.
Okay.
Either or.
So if I understand the question correctly, we're talking about a heatless dryer desiccant life versus a heat reactivated dryer's desiccant life. And in fact, the desiccant life will be shorter on a heat reactivated dryer, simply because the desiccant is heated. You know, all things being equal, you've got good coalescers in place. The heatless dryer, you can get anywhere from, I'd say, it runs the gamut, 3 years, 5 years, 8 years, depending on, you know, the customer and the flow and pressure and temperature conditions of the inlet air. On a heat reactivated dryer, I'd say you'd get 3 to 5 years, and that's simply because of the thermal stress that's put on the desiccant. It's heated up to 400 degrees F, then it's cooled down, then it's heated up. That repeated heating and cooling takes away its affinity for holding vapor. So again, it becomes very important to evaluate any heat reactivated dryer you should happen to look at based on how reliable the demand cycle system is, because the demand cycle system will reduce the number of times you have to regenerate that dryer or expose the desiccant to that heating and cooling. Does that answer the question? I guess.
I think that's quite thorough, Russ, and I agree with you. You know, it is so important that in certain industries we see that customers just put the dryer on a fixed cycle, and their logic is that, you know, since there's less moisture on the desiccant bed, they'll heat up quicker, regenerate quicker, but they don't take into consideration that they're destroying their desiccant by regenerating on a fixed basis. They should try to do it when it's required. So it is sort of critical that you have a very efficient or reliable method of assuring that you relatively load down your desiccant bed before you heat it, so you're not just heating it prematurely. Yeah. Does that conclude the questions?
Yeah, that seems to be about it. If there's any other questions, you can you know, email both Zenon or whomever, and we'd be happy to answer it after the fact.
And we look forward to seeing the registers or the people that have attended. We'll be having a round 3 in mid-September. And if you access the John Brooks site, you can see our schedule of upcoming webinars, and they consist of, you know, compressed air purification. And Nico has a great presentation on pressure vessels. We have Ross McGowan. He covers our heat exchangers. Anita covers liquid filtration. So it's just a knowledge-based location where you can increase your competence in various design aspects of filtration. So I thank you for your time, and look forward to having you again in September.
Thank you.
Thank you all.